In this presentation, we have talked about the types of superconductors. Superconductors are classified into two types. They are type 1 and type 2. Type 1 superconductors are called soft superconductors, whereas type 2 is called hard superconductors. The classification is made on the basis of Mason effect. We talked more about the Mason effect in the previous lecture. Now we will make the recall about the same. Say a superconducting specimen is taken and is placed in a magnetic field and maintain the magnetic field value greater than the critical field. Also, the temperature of the specimen is greater than the critical temperature. Now the magnetic field lines are allowed to pass through the specimen and the superconductor is changed into a normal conductor. If you reduce the temperature of the specimen to a value lesser than the critical temperature and decrease the magnetic field value to a value lesser than the critical field, the magnetic field lines are not allowed to pass through the specimen. They are expelled from the interior of the specimen. Now, this sphere is acted as a superconductor. If the temperature is greater than the critical temperature and the magnetic field is greater than the magnetic field, the superconducting material is acted as a normal conductor. Once the temperature is reduced to a value lesser than the critical field and the magnetic field strength is reduced to a value lesser than the critical field, the same specimen is acted as a superconductor. Therefore, the magnetic field lines are not allowed to pass through the specimen. This is the value of B. B equal to mu naught into H plus M. H is the field applied. M is intensity of magnetization. Take this H outside. Mu naught into H equal to 1 plus M by H. We know the magnetic susceptibility chi equal to M by H, intensity of magnetization to the field applied. Then B equal to mu naught into H into 1 plus chi. According to Meissner, if it is having the superconducting property, the value of B inside the specimen is 0. Therefore, mu naught into H into 1 plus chi equal to 0. From the above equation, it is noted that either the term mu naught into H or 1 plus chi should equal 0. But mu naught into H not equal to 0 because we are applying the field. Therefore, the quantity 1 plus chi is equal to 0. If 1 plus chi is 0, then chi equal to minus 1. The susceptibility is having a negative value. Negative susceptibility is possible for the diamagnetic materials. Then we may say that all superconductors are diamagnetic in nature. If I say a superconductor, it should have the diamagnetic property. Now, come to this statement. Type 1 superconductors obey the Mason effect completely. See this graph? The x-axis represents the magnetic field applied, whereas the y-axis indicates opposing magnetization. The meaning of negative sign is, if you apply the magnetic field, the magnetization is opposed by the specimen, which means that the magnetic field lines are not allowed to pass through the specimen. That's the meaning for this negative sign. If you increase the applied field value gradually, once the field value is equal to the critical field, this opposing magnetization drops to 0 suddenly. That means, if the field value is gradually increased, the magnitude of opposing magnetization is also increased. This means that the substance is maintaining its diamagnetic property up to the critical field. If the critical field is reached, the magnetization drops to 0. That means the magnetization is reaching the positive quantity, approaching towards the positive quantity. Therefore, the diamagnetic nature of the superconducting material is changed into paramagnetic because of the positive susceptibility value, less positive. So the field applied is lesser than the critical field, it obeys the Mason effect. If the field value is exceeding the critical field, it does not obey the Mason effect. Now read out this statement. The graph shows that the intensity of opposing magnetization equals the magnetic field applied up to the critical field. Therefore, magnetic field lines are not allowed to pass through the specimen. Once the critical field is reached, the intensity of magnetization suddenly drops to zero. Here the diamagnetic property is changed into paramagnetic. Now the superconductor is changed into a normal conductor. Type 2 superconductors obey the Mason effect partially. See this graph, here we are having two critical field values. If the field value is lesser than HC1, the specimen is acted as a superconductor perfectly. It obeys the Mason effect completely in this region. If the field value is reaching HC1, the magnetic field lines are started to penetrate through the specimen gradually. But in this case, if the field is approaching HC, the magnetization with a negative sign drops to zero. Here it is not dropped to zero suddenly, but it is decreasing gradually. If the field value is greater than HC1, the magnetic field lines are started to penetrate. In between HC1 and HC2, the substance is in the mixed state, partially superconducting, partially normal conducting. Once the field is exceeding the value of the second critical field HC2, it is switching over to the normal state. The material is a normal conductor. So that if the field is lesser than the critical field, it obeys Mason effect perfectly. In between HC1 and HC2, it's not obeying perfectly because the magnetic field lines are passing through the specimen. Now read out this. Type 2 superconductors have two critical fields. When the field value is lesser than the first critical field, that is HC1, the intensity of opposing magnetization should equal the magnetic field applied. This means that the magnetic field lines are not allowed to pass through the specimen if the field is lesser than HC1. Beyond the first critical field, the magnetic field lines started to penetrate the specimen and the material was in a mixed state. When the applied field exceeds the second critical field, the material is completely transformed into a normal conductor. But in the case of type 1, if the field is lesser than the critical field, the magnetic field lines are not allowed to pass through the specimen, B equal to 0. Then after HC, that is the field value is greater than HC, B not equal to 0. Here less than HC1, B equal to 0. But in between HC1 and HC2, the magnetic field lines are started to penetrate gradually. But the specimen is in the mixed state, partially superconducting, partially normal conducting. And the second point is, type 1 superconductors have a low critical temperature. The value of critical temperature is less for the type 1 case. Critical temperature means if the temperature of the specimen is maintaining a value lesser than a particular temperature, the nature of the specimen is superconducting. If the temperature of the specimen is exceeding that particular temperature value and the specimen is changed into a normal conductor, that particular temperature is called critical temperature. The type 2 superconductors have a higher critical temperature. And type 1 superconductors have a low critical field. If you apply lesser field, you may convert the superconductor into a normal conductor. If you provide high field, even though the material is not changed into a normal conductor. Therefore, type 2 superconductors have a high critical field. These are the examples of type 1, mercury, lead and Zn. They are pure metals, but type 2 superconductors are alloys, metal with non-metal or metal with non-metal with metal are called alloys. Alloys like niobium tin, niobium titanium, niobium zirconium are the examples of type 2 superconductors. Because of less critical field, type 1 materials are not used to fabricate electromagnets, but we can use the type 2 materials to fabricate electromagnets. That's all about the major differences between type 1 and type 2 superconductors.